So today's focus is going to be finding theoretical probability. All right, so there's basically two types of probabilities that we're going to focus on, and that's theoretical probability as well as experimental probability. So I'm going to just explain the theoretical probability, but for theoretical, it's everything that's supposed to happen if the total number of outcomes is equally as likely. Okay? But for an experimental probability, that's what actually happens in an experiment. What's the probability in an actual experiment? So for theoretical, is just what you should get, what should occur, versus experimental, which gives you data already. Okay? So if that sounds a little bit confusing, don't worry about it. We'll focus on theoretical today and experimental tomorrow. So the sample space is a set of all possible outcomes for an event. A sample space can be small, such as the two outcomes when a coin is flipped, or a sample space could be large, such as the possible number of Texas Classic automobile license. Okay? So whenever we're doing probability, we always have to identify the sample space, which can help us calculate that probability. So let's go ahead, let's go back for a second. All right, so a sample space could be as small as two outcomes when a coin is flipped. When you think about a coin, right, there's only two possibilities that you have. You have either heads or you have tails. So that means the sample space has two outcomes. Now, for this larger example over here, for the Texas Classic automobile license plates, you can imagine that there's millions of drivers in Texas. And with those drivers come their cars. And with those cars comes different variations of license plates. So the sample space there is really, really large because license plates are not supposed to be identical. Okay, so think about a sample space as what is the total possible outcomes or what can happen in a given situation. So in order to calculate this mathematically, we use the formula P event is going to be equal to the number of times the event can occur, or the event actually occurs, over the total number of equally likely possible outcomes. All right, so let's actually do an example so you can understand this a little bit better. What is the probability of rolling an even number on a standard number cube? So the first thing we have to do here is find the sample space for a standard number cube. A standard number cube, as you can see over here to your right, has the numbers. You could either roll a 1, a 2, a 3, a 4, a 5, or a 6. So we could say here that there are 6 possible outcomes. Okay? So that is my sample space. My sample space is 6 outcomes. The sample space specifically is 1, 2, 3, 4, 5, and 6. All right, so next, I'm going to find the number of ways to roll an even number. So of course, 2 is an even number, 4 is an even number, and 6 is an even number. So we could say that the event can occur, O-Z-C-U-R, 3 ways. Okay, that's either if I get a 2, a 4, or a 6. So now I'm going to use the formula to find the probability. So to find the probability, we have P even number is equal to the number of times the event can occur, which is 3, over the total number of equally likely possible outcomes, which is 6. And always, always, always simplify. So 3 over 6 is going to be equal to 1/2. Okay? So we could say that the probability of rolling an even number is 1/2. Or we could say 0.5, or we could say 50%. Okay? So all that means, if we look on our little number line that we learned about the other day, it's going to be as likely as not to happen, getting an even number. Let's go ahead and move on to a couple more examples. Once again, theoretical probability is what you can expect to happen in a specific event. It's not necessarily what actually happens, but it's what should happen if everything else is equal. So picking a purple marble from a jar with 15 green and 10 purple marbles. So what is my sample space? My sample space is 15 green and 10 purple. All right, so in total, I have a total sample space of 25 marbles. Okay, so picking a purple marble from a jar is going to be 10 over 25. Okay, so this is my number of times the event can occur over the total number of equally likely possible outcomes. So once we go ahead and simplify that, divide by 5, we're going to get 2/5. So 2/5 is equal to 0.4, which is equal to about 40% likelihood of happening. So if we look on our spectrum from 0 to 1, all right, it lies somewhere over here. So this is most likely unlikely going to happen. Okay? Now, rolling a number greater than 4 on a standard number cube. So our sample space is 1, 2, 3, 4, 5, 6. Those are the only possible numbers I could roll. So a number greater than 4. It can't be 4 because it doesn't say greater than or equal to 4. So my only other two options is 5 and 6. So the number of times the event can occur, so P greater than 4 is going to be equal to 2 over 6, which simplifies to 1/3, which is equal to 0.33 or 33%. 33.33% because it's a repeated number. Okay? Let's go over our last event. Now, we mix it up for probability. Sometimes we're going to focus on cards. Sometimes we're going to focus on coins. Sometimes we're going to focus on rolling dice. There's plenty of examples and situations in which we could come up with probability. So I'm trying to show you as much as I can. Now, using the complement of an event. So the complement does not mean that someone is complimenting each other. I heard that response multiple times yesterday. So the complement of an event is the set of all outcomes in the sample space that are not included in the event. For example, in the event of rolling a 3 on the number cube, the complement is rolling any number other than 3, which means the complement is rolling a 1, 2, 4, 5, or 6. So basically think about it as the opposite of what you're trying to find. So of course, if we were trying to roll a 3, that would be 1/3. Okay? But we don't want that. We want the 1/3. I'm sorry, 1/6. And there's 6 possible outcomes. But we don't want that. We want the complement. So the complement of 1/6 is going to be 5/6. 1/6 plus what number is going to equal to 1? 1/6 plus 5/6 is going to be equal to 1. Okay? So this is the formula we're looking at, an event and its complement. So the sum of the probabilities of an event and its complement has to equal to 1. So the event, which is 1/6, plus the complement, which is 5/6, has to always be equal to 1. All right? In this case, it's going to be equal to 6 over 6, which of course is equal to 1. All right? Now, let's take a look at this example with a standard deck of cards. There are 2 red jacks in a standard deck of 52 cards. This jack of hearts right here and this jack of diamond right here. All right? What is the probability of not getting a red jack if you select one card at random? So I want to know the probability of not getting a red jack. So if you see that not there, it's basically asking you to find its complement. Okay? So we have a formula, P event plus P complement is equal to 1. So P red jack plus P not red jack is equal to 1. So what is the probability of getting a red jack? There's only 2 of them. So it's going to be 2 out of 52. Plus P not a red jack. Okay? All of that is going to be equal to 1. All right? But instead of putting 1, I'm just going to put 52 out of 52 so I could have common denominators and just subtract the fraction instead of converting it to a decimal and having to divide and do all of that. Just keep it as a fraction for now. Okay? So in order to figure this out, just do algebra. Subtract 2 over 52 on one side and then subtract 2 over 52 on the other side. This cancels out. I'm left with P not a red jack is going to be equal to 52 minus 2, which is 50 over 52. When we go ahead and simplify that, it simplifies to 25 over 26. Okay? So I would say in this case, the probability that you will not draw a red jack is 25 out of 26. So it is likely that you will not select a red jack here. Okay? And that's how using the complement of an event works. We'll do a lot of practice with all of this stuff in class tomorrow.